Good morning, everybody. So let's get started on this second day of lesson 3.4, the chain rule. So first of all, I don't know if any of you have started I wanted you to start the lesson, the assignment. Did you have some problems you would like me to go through or talk about? All right, well, I'm not hearing anything, so we'll move on. So I just want to remind you of this slide. When you have repeated, you have to really watch when this happens, repeated application of the chain rule. You're going to see one today, I think, that has 4 or 5 repeats of the chain rule. This one doesn't, but it does have a chain rule. So if we do the sine cubed of 4t, of course that means the sine of 4t cubed. We first of all on the outside do the power rule. Hi Jessica, welcome. So you first do the power rule, 3 times the sine of that 4t squared, and then what's the derivative of the sine? Cosine. And so you see we're at the second stage, cosine 4t. Oh, but there's a chain rule of second again, because 4t is itself a function, and the derivative of 4t is 4. So the red line finally has all of the chain rules executed, and then you just combine things. 3 times 4 is 12, and just put things into one simplified expression. So just a reminder, the chain rule can occur over and over again. So it's almost like you have to keep asking yourself the question, wait a minute, is there an inner function that I should be dealing with? And it never hurts to go too far, because if you go too far, the next time you'll be multiplying by 1, and it certainly doesn't hurt to multiply by 1. All right. So where are we? Okay. So I believe I showed you this last time. I don't remember. It's a little bit different with the second section, but we learned that the derivative of the natural log is 1 over x. Am I right? We talked about this last time. Anybody? Does anybody recall?
No.
I don't think that we did, no.
Okay. So here's a new derivative for you. The derivative of the natural log of x is 1 over x. So that only works with a natural log. We'll talk more about other kinds of logs in a few moments here. So the derivative of a natural log is 1 over x. And then number 2 just says, hey, don't forget, you may have a chain rule here too. So what if you take the natural log, for example, of 2x? Well, it's 1 over that thing, 1 over 2x, and then chain rule, 2x has a derivative of 2. You'll see, we'll do some right now. Yeah, first of all, I'll just show you, I don't normally show you proofs, but I want to show you the proof that this is true. At the very top, there's our function, the natural log of x. What does that mean? Y equals the natural log of x. What is a natural log? It's that number which, when placed on e, gives you the result of x. And you can see that in this second line right here. You know, that number, y is that number when you place it on e that gives you x as an answer. So here's the other way you can express that. So let's take the derivative of both sides. The derivative of the left equals the derivative of the right side. Well, the left side, what's the derivative of e to the y? Now we know what e to the x is. That's e to the x. But what's e to the y? Well, I don't know. What is y? Y is itself an equation, so we need to do the chain rule. So what's the derivative of e to the y? Itself, e to the y. And then we got to take the derivative of y with respect to x because we don't know, we don't quite know what that is. And on the right side, the derivative of x, that's easy, 1. Let's divide both sides by e to the y, and you get dy dx equals 1 over ey. And what's e to the y? Oh, that's x. And you can see the derivative really is, the derivative of the natural log really is 1 over x. Okay, so that's a new one for your memory work. So let's apply that. And yeah, so instead of their work, I'd like you to kind of look over to the right side here. So here's the derivative of 2x. I'm sorry, the derivative of the natural log of 2x. Now, I just showed you what the natural log of x is, 1 over x. So what's the derivative of the natural log of 2x? It's 1 over that thing. So look over here at the right, 1 over that thing, 2x. And then we have a chain rule, right? Because 2x, that's an inner function. And what's the derivative of 2x? 2. So to finish this off, we have 1 over 2x times chain rule, 2. The 2's cancel. And it turns out that in this case, it's actually equal to the same answer as the natural log of x. Don't think of that as a pattern, though. But here, let's take a look at the second one. What's the natural log of x squared plus 1? Again, it's 1 over that thing. It's 1 over, looking over here to the right again, it's 1 over x squared plus 1. And then x squared plus 1 is an inner function. What's the derivative of x squared plus 1? 2x. So by chain rule, we multiply by 2x. And you can see the answer is back over here, 2x over x squared plus 1. Let's look at part C. What's the derivative of x times the natural log of x? Well, that sounds like a product, right? X times natural log of x. So product rule. First, x times the derivative of the second plus the second times the derivative of the first. And what is, now let's fill in the blanks. What is the derivative of the natural log? We know that's 1 over x, so x times 1 over x plus, and what's the derivative of x? That's easy, 1. So, end result, 1 plus the natural log of x. Let's do one more. Part D, the natural log of x quantity cubed. Let's take the derivative of that. Well, the outside function is a cube, so we first have to do a power rule. Multiply by the exponent 3, then keep the same quantity, reduce the power by 1. Now we have the inner function, natural log of x. What's the derivative of the natural log? 1 over x. I'm not real thrilled with the way they wrote that. I would have written it like this. Just algebraically, I would have said 3 times the natural log of x squared. And I would just put it over x, but it's the same as what they've got. So let me just pause a few moments. Any questions?
In example D, is it like 3 times the natural log x squared? Is that multiplying by the natural log x? Is that, and that's how you get the final product?
That means 3 times the natural log of x times the natural log of x again.
Okay.
So it's literally whatever the natural log of x is, that has to be multiplied by itself.
On the test, will you, will the question say, use the quotient rule to figure this out, or are you just going to give us a problem and expect us to know which rule to use?
Yeah, you're going to have to know which rule. You're going to have to, I'm expecting you know which rule to use. How did I know which rule to use? Well, what's on the outside here? an exponent. So we got to start with the power rule.
And when's our next like test for this chapter?
At the end of the chapter. When will that be? I know not yet. It's too early for me to tell.
How early in the week will you try to cut off new material so we can review before the test? Because this is a pretty long chapter to remember everything.
At the most, what I'll do is we'll have 2 days of review.
Okay. Would you be able to make one of those days of review not on the online class so we can physically be there to work stuff out with like the whole class?
The whole class can be here to work things out online too. But okay. I don't know. That all depends on how the timing works out.
Okay.
If the test falls toward the end of the week, well, then then we're gonna we'll be in person. It all depends how Tuesday matches up with, and I don't do any of that intentionally. I just see when we reach the end. So let's just wait. Let's see how the end of the chapter shakes out, and then we can try to answer those questions.
Okay.
Now, you remember your log properties? Because your log properties can help you out a lot. Here's an example. It says, differentiate the natural log of the square root of x plus 1. Well, the first thing let's rewrite the square root of x plus 1. For calculus, it's better to write that as what? X plus 1 quantity to the 1/2 power. We're used to that. Okay. So if this is our, let's just change this. So if this is our thing to differentiate now, what do we do? Well, okay, let's see. We've got, one of the log laws is what happens when you take the logarithm of something to a power. The rule is take the power and multiply it by the logarithm of the base. And that's what you'll see in this first line. What's the power? 1/2. Take that times the natural log of the base, the x plus 1. So there's no calculus here. This is strictly, algebra log rule. Okay, now we're ready to do a derivative. What's the derivative of this right box? Well, we got a constant in front. You already know. Just leave that be. So there it is, 1/2. And then, what's the derivative of the natural log of something? It's 1 over that thing you're taking the natural log of, 1 over x plus 1. And then, see if you have a chain rule. Do we have a chain rule here? Is there an inner function when you're doing the natural log of x plus 1? Actually, there is. It's x plus 1. What's the derivative of x plus 1, though? 1, right? So
why isn't it 1/2 times natural log x plus 1 to the negative 1/2? Because don't you have to do the power minus 1? Or does the natural log just take care of putting the x o?
There's no okay. I see I can see where the confusion is. Let me do some erasing here. Okay, so in this first part, there is no derivative right there. We didn't do anything. Is there a derivative here? No, that's just using a log law. We haven't done a derivative yet. When you take here, all right, when you take the log of x squared, how do you do that? The log law says that's 2 times the log of x. There's no calculus there. That's just algebra. That's a log law. So what I did in the box right here is just apply the log law. Now, down here is where we do the derivative. Okay, now we're actually doing a derivative. Keep the constant there. The derivative of the natural log of something is 1 over that thing. And then times, we really are multiplying by the derivative of x plus 1, but the derivative of x plus 1 is a 1. So we did times 1 isn't there because, you know, nothing happens when you multiply by 1. So I don't know if I helped, but maybe there's a little bit of fogginess about log laws. I don't know.
So with the log law, you don't have to do the -1 for the power. You just put it in front of the log.
Yes, correct.
And that's only for the log rule. Otherwise, you have to do the power -1.
No, okay. When you're doing a derivative, you have to do that power -1 thing. Okay?
Yeah.
But we're not doing a derivative in the box. That's just algebra up here. This is just simplifying it before we start. The derivative is down here, and that's where we did the 1 over the thing. All right, let's take a look at another one. Yeah, so here's a here log laws help you out quite a bit. Let me do some erasing so that I can try to point things out a little bit without being interrupted. All right, so here we're supposed to differentiate the natural log of, and this algebraic fraction, this x times x squared plus 1 quantity squared, divided by the square root of 2x cubed minus 1. Wow. Okay. There's a lot going on there. Let's not do calculus yet. Let's just do log laws. And do you remember how those log laws work? Like, what happens when you take the log of a product? What's the log of x times y? It's the log of x plus the log of y, right? What happens when you do the log of x divided by y? That's the log of x minus the log of y. And we just did the other one. What happens when you take the log of something to a power? You just take the power and multiply it by the log of the base. So this line right here is doing nothing but, there's no calculus there, but just log laws. So on the top, we have the log of x plus 2 times the log of x squared plus 1. Why is it plus? Because x is being multiplied by x squared plus 1. Why is it 2 times the log of x squared plus 1? Because of the log law that when you take the log of something to a power, you bring the power out in front and take it times the log of the base. And then why are we subtracting the log of that denominator? Because we're dividing. Why is it 1/2? Well, because it really, I mean, this thing on the bottom is really what? 2x cubed minus 1 to the 1/2, right? Because it's a square root. Yeah. And how do you take the log of that? 1/2 times the log of the base. So now, what's cool about that is we have just a bunch of things being added and subtracted instead of this complex mess we had up here, where we have division, powers, all kinds of crazy things going on. So the log law is really simplified. Now let's do the derivative down here. What's the derivative of the natural log of x? 1 over x. What's the derivative of 2 times the natural, well, 2, that constant, don't do anything with that. The natural log of something is 1 over that thing, so that thing, x squared plus 1, goes to the denominator. Why is there a 2x on the top of this one? Chain rule, right? So we've got 1 over that thing, 1 over x squared plus 1. And what's the derivative of x squared plus 1? Oh, 2x. So we have to multiply by 2x. That's how that got up there. Then the rest, keep the constant out in front of this one. What's the derivative of the natural log of something? It's 1 over that thing. So you see, there it is on the bottom. And the chain rule for 2x cubed minus 1, what's the derivative of 2x cubed minus 1? 6x squared. So that's why that winds up on top. So quite a bit easier than tackling the thing at the top of the screen. So whenever you have a natural log problem or a log problem, you see that was a natural log problem up there, you want to use log laws to simplify it before you do a derivative. And that's what we did up until the wavy line there. The rest of this is just algebra simplification. 2 times 2x is 4x. Negative 1/2 times 6x squared is 3x squared. So not much going on in that last line. This is not calculus either. This is a log law. When you take a log to another base, see, up until now we've been doing natural logs. And what's a natural? A natural log is with base e. But what if they ask you to do a log base? Sorry, a little technical difficulty here. But here we have a log base a, right? See that little a there? The log base a of x. So the log base a could be anything. And I don't like the way they wrote it there. This is off to the right is makes a little more sense. So the logarithm base a of something is the natural log of x divided by the natural log of a. And that turns it into a natural log problem. So even when it's not a natural log problem, this will make it that. All right. Last new thing we've got. So these 4 things actually are somewhat the same. But number 1, what if you want to take the derivative of some other, not e to the x, not 10 to the x, but just any number a to the x, except for a being 1, because 1 to the x is kind of stupid. 1 to the x is just 1, and we already know what the derivative of 1 is. It's 0. So the question is, what about when a is any number other than 1? Well, here's the answer. The derivative of any number a to the x is itself multiplied by the natural log of its base. Itself, so almost like, you remember this one? Here, let me try to get my pen working here. Make this a little bit bigger. So all of you remember this one, right? The derivative of e to the x is e to the x, right? So what's the derivative of e to the x? Itself. What's the derivative of a to the x? Itself multiplied by the natural log of a. By the way, that works down here too. It's actually, what's the derivative of e to the x? E to the x times the natural log of e. What's the natural log of e? What exponent goes on e to give you e? 1. So really, this is e to the x times 1, and that's why it's just e to the x. So, in the beginning, I told you it's the easiest derivative. It is, but it's because of this principle. So really, this is the same thing. It's saying any number to the x itself times the natural log of its base. And then number 2 is just the same thing, except it's saying, don't forget, if this exponent, let's see, all this is saying is you may have to do the chain rule. if there's an inner function. That's all that's saying. Number 3, all right, what if you take the log to any base, a, not just the natural log, but to any base. I got to get rid of that because you can't even see it. So, and the answer is, just like before, remember what's the derivative of the natural log? 1 over x. What's the derivative of any log? It's still 1 over x, but on the bottom also multiply by the natural log of whatever a is. So if we were taking the log base 10 of x, it's still 1 over x, but on the bottom we'd also multiply by the natural log of 10. And the number 4 is just saying you may have to do the chain rule. So these are our last 2 new ones. Let's just go over them one more time. They're over here on the left. The derivative of any number a to the x power is itself multiplied by the natural log of whatever that base is. And when you're doing the derivative of the log any base of x, 1 over x, and on the bottom multiplied by the natural log of whatever that base number is. Well, maybe we just let's look at some examples. Yeah, first of all, I've already done this, but let's just take a look at it again. So if we have a function a to the x, what's its derivative? Itself, a to the x, multiplied by the natural log of its base, a. And the bottom is just showing you, hey, that works with e to the x. I've already done this, but here we go. So what's the derivative of e to the x? Itself times the natural log of its base. Well, the natural log of e is 1, and so this derivative is wonderful. It just turns out to be itself. Okay. So here's a couple examples using those new laws we just talked about. Okay, let me make this a little bit bigger. So, a, what's the derivative of 2 to the x? Itself, 2 to the x, multiplied by the natural log of 2. And the natural log of 2 is just a number. But that's your answer right there. We could actually look up the natural log of 2 and get a number for that, but we're happy with that. How about b? This time, we're supposed to find the derivative of 2 to the 3x power. Notice the inner function up there, 3x. So this one we're going to have to do the chain rule on. So anyway, how do you take a constant to a power? Itself, 2 to the 3x, times the natural log of its base, natural log of 2. And now the inner chain rule, 3x. Oh yeah, the derivative of that is 3. Now we got it all done. And then just rearrange it a little differently, put the 3 out in front. And that's it. I'm going to pause, see if you have comments or questions.
Where did you get the derivative is 3 from?
From right here.
Oh, right. That's the inner function. Okay.
Yeah, it's that power where there was a 3x. So that was the inside of this thing, okay? The 3x. So I had to multiply by the derivative of 3x. All right, let's take a look at C. Now notice this is not a natural log. This is a log base 10. The log base 10 of the cosine. So we're supposed to take the derivative of that, right? So how do we take the derivative of the log base 10? Well, it's 1 over that thing that we're taking the log of, cosine x. See how it's on the bottom there? And then we got to multiply by the natural log of that base 10 on the bottom. Okay, that's the end of the logarithm part. Now the inner function is, what's the derivative of the cosine? Minus the sine. And that's how the minus the sine gets on the top. So the derivative of a log is 1 over that thing times the natural log of that thing's base on the bottom. And then, in this case, we have a chain rule because we have an inner function, cosine x. And when we do the chain rule, the derivative of the cosine is minus the sine. Now, how did they get from here over to the end here where they have minus? So that's just, what's sine over cosine? Tangent. So all they did is say sine over cosine is tangent. They put the minus sign out in front. Otherwise, it's the same answer. So, okay, let's take a look at D. So it says, after rewriting the function below using log properties, then you can go ahead and find the derivative way on the bottom. So this line right here is all logarithms in algebra. We're not doing any derivatives here. So here we go. The log base 3 of the square root of x divided by x plus 5. Well, how do you take the log of the square root of x? Well, that's x to the 1/2. And how do you take the derivative of something to a power? You take the power 1/2 times the log base 3 of the base x. Why are we subtracting? Because it's a division problem. Subtract the log base 3 of x plus 5. So this is all log laws to get to here. We haven't done any calculus yet. Now we're going to do the calculus. So what's the derivative of that whole thing? Well, part 1. What's the derivative of 1/2 times the log base 3 of x? Well, when you take the derivative, first of all, the 1/2 stays out in front, the constant you don't do anything with. What's the derivative of a log? 1 over that thing, 1 over x. But because it's a non-natural log, we got to take it, also multiply down there by the natural log of 3, minus, and then the same thing. The derivative of the log of x plus 5 is 1 over x plus 5. Because it's on log base 3, we also multiply by the natural log of 3. And then to get from here to the part in the circle, that's just a matter of getting a common denominator. You can see we don't have common denominators, right? So this first thing is missing what? An x plus 5 in the denominator. And this one is missing an x. And so if you multiply by those, you can bring them together. That's not really what I was trying to show you here, but okay. So log laws really set the table really well for making derivatives much easier. Well, that's it for new derivatives. You'll see in the book that brings us to this page. It's called the Summary of Differentiation Rules. Let's just go through them. We got the derivative of a constant is 0. The derivative of x to the n, and so this is the power rule up here. The derivative of x is 1. By the way, you can do that by the power rule, right? Because I mean, x to the 1, what's the power rule? Bring the power down, reduce the power by 1. What's 1 times x to the 0? 1 times 1, and you can see, so you could even do that one by the power rule. So the derivative of x is 1. What do you do with a constant? Just leave it out in front. What do you do when you have the derivative of a sum? Just take the derivative of each part and add them together. That's nice. Same with the difference. Okay, then we got, sorry, I have too many marks up here. Let's get rid of some of these. Can't get rid of too much because, okay, that's as much as I can get rid of. Now, then we added the product rule and the quotient rule. Okay, we did those in the previous lesson. Then the last 2 days we've been talking about the chain rule. And because of the chain rule, we know that the power rule can be used with the chain rule depending on, you know, what quantity you're taking to your power. You know, for example, if you're doing x to the third, that's just a simple power rule, 3x squared. But if you're doing 3x to the third power, you would start with the power rule, 3 times 3x, and then quantity squared. But then there's an inner function, and then you'd have to take that times another 3 on the end. So this is just saying the power rule might have a chain rule in it also. Okay, then we have the 6 trig functions. The first 2 are the only ones they gave us, right? Derivative of the sine is the cosine, derivative of the cosine is minus the sine, and then we did these other 4 using the quotient rule. Remember that? We did those in class. We've got good old derivative of e to the x, which is itself. Then here's the new one we had today, derivative of the natural log, 1 over x. What's the derivative of any base to the x? Itself times the natural log of its base. And finally, the derivative of a logarithm to any base is 1 over x. And that denominator has the multiplication of the natural log of that base, whatever that base is. I usually like to write the natural log on the end. They put it on the beginning, but it's all right. So there's our derivatives. Now, so the rest of today, what I wanted to do is do some examples from lesson 3-4. So let's dive into those. So first, I've got number 17 here. Trying to simplify things here. Let's get this out of the way. So this is just what, a quotient rule? Does everybody see that? Why do we have that times 0 on the top? Denominator times derivative of the numerator. Well, the derivative of 1 is 0. Okay, not much to that one. Number 23. Overall, what's the overall outside rule you would use here?
Product rule?
Yep, product rule, because we have x squared multiplied by x minus 2 to the 4th. So, you do the product rule. The first times the derivative of the second. By the way, there's a chain rule there. 4 times x minus 2 to the 3rd, and there's a derivative. But what's the derivative of x minus 2? It's 1. I know, you're probably thinking, I don't need that. You don't, but you need to remember the chain rule. All right. And then the second half of the product rule plus the second times the derivative of the first. Okay? I didn't do much there. I simply, x squared times 4 is 4. I just wrote it in a neater to use format. The 2x, I brought that in the front on the right. Not much algebra there. So here comes that factoring technique that you want to get into. We have 2 terms in this previous expression. Very fat terms, separated by the plus sign. Is there anything in common between 4x squared and 2x? Yeah, there's a 2x that can take, so pull that out. Is there anything in common between x minus 2 to the third and x minus 2 to the fourth? Yeah, x minus 2 to the third. So I pull those two things out. What's left? 2x times, I need a 2x in order to get this 4x squared back. What do I need to take times x minus 2 cubed to get x minus 2 to the fourth? I got to take it times x minus 2. You're probably wondering, why did we do that? And the answer is the next step. Because now, simplify what's in the brackets. Oh yeah, that just can be written as 3x minus 2. And now you're done. I'm going to pause a little bit, see if anybody has a comment or a question on number 23. Or maybe wants, if you want to write it down. Okay, now let's go on to the next one. Next one I've got is number 30. All right, so we got something squared. Now here's a case where I use some algebra as my first step. Why don't we just square the top and the bottom? And that's what I did. T squared is t to the fourth. T cubed plus 2 squared. Okay, now let's go ahead and let's do the derivative. So this is what? Quotient rule, denominator times derivative of numerator minus numerator times derivative of denominator. Chain rule. See, here we didn't have to worry about a chain rule because derivative of numerator, there is no inner function. It's 4t cubed. But when you take the derivative of the denominator, power rule, 2 times t cubed plus 2 to the 1 power. Oh, t cubed plus 2 is a function, an inner function. The derivative of t cubed plus 2 is 3t squared over denominator squared. Didn't do a whole lot there. I just rewrote the order of this, and when you take 3t squared times negative 2t to the fourth, you get negative 6t to the. So I just brought it together a little bit on the top. Now we have two factors on the top. 4t, this 4t one here and this 4t cubed one and the negative. So two terms. Do we have anything in common we can take out? Yeah, between 4t cubed and 6t to the sixth, we could take out 2t cubed. There it is, over here on the left. Can we take out anything from t cubed plus 2 to the second and t cubed plus 2 to the first? Yeah, we can take out t cubed plus 2 to the first. What's left? What times that? Okay, we need a 2. And we need another t cubed plus 2 in this first term because there were 2 of them. On the end, we only need, what, a 3 and a t to the cubed, and we don't need any t cubed plus 2 because we took the whole thing out. Now simplify the parentheses. 2t cubed minus 3t cubed is negative t cubed. And 4 from multiplying out the distributive property. By the way, the circles indicate either one of those last two expressions probably would be fine. I would give full credit to both answers. And honestly, I don't know which one's in the back. Probably one of these is in the back, but both of these are correct. So does anybody have a question on that one? Or a comment? So there's a case where some algebra in the very beginning was a wise move. Otherwise, you'd have had a much more, you'd have had another embedded chain rule in there, and you can greatly simplify it by doing some algebra first. Okay, let's go to the next. The next one I've chosen is number 50. And this one, this won't take long. The secant of x squared. I put parentheses around x squared because that's what's meant, right? The secant of that whole, that x squared part. Please note that this red is what you don't want to think of it as. This is not the same as secant squared of x. Secant squared of x means secant x times secant x, which is not what this is. So anyway, all right, so how do you take the derivative of the secant squared? The secant of x squared. Well, we learned that the derivative of the secant is the secant of that thing times the tangent of that thing. So secant x squared, tangent x squared. And, oh yeah, x squared is an inner function, the derivative of x squared, 2x. So very important that this part be on the end. Okay, let's go to number 60. Number 60, g of theta equals cosine squared of 8 theta. We are supposed to differentiate. So first of all, would you agree with my algebra simplification that you currently see? What does cosine squared of something mean? It means cosine of that thing times, it means this thing on the right. So one of the unfortunate things about some of the shortcuts that we have in trig is that they need clarification before we do a derivative. So anyway, we've got that done. So what's the derivative of the cosine of 8 theta squared? Well, first of all, it's a power rule on the outside. 2 times the cosine of 8 theta to the first power. There's the power rule. What's the derivative of the cosine? Oh, minus the sine. Well, we're not done yet because there's another embedded function in here, 8 theta, and the derivative of 8 theta, 8. So here we have 2 chain rules that have to be done. Little pause again. Comment, question?
Are these slides like available for us to see in full or just like the video online?
To see in full.
Like, could we go back to these and like reference them, or are we only allowed to look at the YouTube video and the problems that you saw?
I believe they're available for the most part. So for example, if you go to the website, which I'll do real quickly here. And then if you go down to section, well, what are we on? Lesson 3.4, right? So you see how we're on 3.4? No, yeah, right here. 3.4, the chain rule. Notes. And if you click on that, most of these slides are available. I mean, we're not in the right place here on the slides, but yeah, like, see, there's a slide we looked at. So I would say most of them are there, but they're not all there. Okay. So go to the website. We aren't done with this. The only thing you got to do after this is just bring it all together. 2 times 8 is 16. Why is it negative? Because the sign, the negative sign in here. And now we're done. Let's keep going here. Let's do a couple more. How about this one? The cosine of the square root of the sine of the tangent of pi x. Whoa, have we got some embedding going on here? So the first thing, would you agree with this rewriting? the cosine of the sine of the tangent of pi x to the 1/2 power. So it's just another way to write the square root, right? Okay, now, what's the derivative of the cosine of something? Yeah, minus the sine of that thing. So minus the sine of the tangent of pi x to the 1/2. What's the next thing we have? Oh, the power rule, 1/2. Okay, so we have to do the chain rule times 1/2, and then reduce the power by 1. Okay. And what's the derivative of the sine of something? Oh, the cosine of something. Oh, and that's not it. What's the derivative of the tangent of pi x? That's the secant squared of pi. Oh, and pi x is still a function. So what do we got here? We've got 1, 2, 3, 4, 5 embedded chain rules here. So I would just urge you, don't ever quit until you're convinced there's nothing left on the inside. This last thing, what's the derivative of pi? That's 0. Anytime you get 0, that would zero out the whole thing. That's certainly, you don't have to go that far. But see if you've got, if you got any variables left, like we do here, pi x, then you got to go another step. So watch the embedding. So that one takes the award for the most for the most embedded one and the most chain rules. Okay, here we just have a product rule. X squared times e to the negative x. So we use the product rule first times derivative of second. Chain rule. Did you see that one? Watch out. Negative x, negative 1 times x, derivative negative 1, plus the second times the derivative of the first. And then, okay, how do we write that? Well, e to the negative x, that means e to the x on the bottom. Yeah, because they already have a common denominator, you can bring them together. So that one turns out to be pretty mild. But did you spot that chain rule? Got to get your chain rule. You got to always watch for the need to do the chain rule. So we're over time here. Let's just do this one. I don't know. I got a bunch to do yet, but which one do you want to do? You got 86, 91, 93, 129.
I think we should do 91.
That wins that's fine with me. So here we go. We have the natural log of x over x squared plus 1. Okay. How do you take the derivative of a natural log? It's 1 over the thing you were taking the natural. How do I take 1 over a fraction? Answer, just a reciprocal. So what's 1 over x squared plus 1? X squared over 1 plus x over x. Okay. Now, unfortunately, we have quite a chain rule to do because inside this function there is a quotient. So we got to do the quotient rule. So denominator times derivative of numerator minus the numerator times the derivative of denominator over denominator squared. So it's not very hard, but and then just a matter of doing a little bit of simplifying, a little bit of canceling happens. Here's a case where the x squared plus 1 on the top here cancels with one of the two x squared plus 1s in the denominator. And so I'll let that one up there for a few seconds. Anybody have any comment or questions? I think we're gonna we've been over for about 5 minutes here, so I'm going to hang it up. Questions or comments? So don't forget now, you got that 3-4 assignment for tomorrow. Should I remind you of that?
Are you gonna collect 3-3 too? Because you never collected that yesterday.
I didn't. I only collected one assignment so far.
Okay.
So no, I did not collect 3-4, and I don't tell you when I'm going to collect. In fact, I don't even know. I usually decide that day.
All right.
Sorry, can't tell you. The assignment, yeah, here it is. So just a reminder, what needs to be done on 3-4. So unless you have another question, I'm going to just let this up for a few minutes so you can get it in case you haven't gotten it from the website. Otherwise, we are done. Thank you for your attendance. Okay, I'm going to terminate the broadcast. Thank you.